Hey everyone, I'm Moin. This is the first video I'm recording for YouTube, and I'm a machine learning engineer. Currently, my focus of work is on recommendation systems, but basically I've been using LLMs for different applications at my current job, my previous job, and my graduate studies. And I wrote a blog post about LLMs as retrieval and recommendation agents on Medium a while ago, and today I was hoping to go to the topics there with more depth and talk about like a few things I couldn't like really include in the blog post because I didn't want it to get too long. So without further ado, let's start with the blog post and talk about some of the ideas, and I'll try to do a little bit like annotations. Hopefully I can show some of the ideas for a better, more intuitive understandings. Okay, so then if you're interested to read the blog post yourself, and maybe for future reference you want to go back to it, I'll include the links to the blog posts as well. And today I will cover only the first blog post, but in another video we'll do the second part. Okay. So as I mentioned, I've been using LLMs for the past year as my focus to basically see how we can utilize them for recommendation and retrieval systems. And this is kind of a knowledge dump, like everything I had learned. I just wanted to like put it in one place for people to be accessible and kind of do a knowledge transfer. So let's see. So let's start by what is a retrieval and why it matters at all. So retrieval means you have a large collection of things, and what you want to do in a sense is you want to pick a few items that are more related to the task at hand. That's basically the general idea of retrieval. Selecting a relevant number of items from a huge corpus. And this can be the URLs on the internet. There are trillions, I'm sure even more URLs, or books in a library, or products in an online store. You want to retrieve the most related items from a large like data set. And we have a lot of examples of this, like for example Google, like whenever you search something in the query, like for example if this is like Google search box, you have your query here and you say, hey, I want to find, let's say, hey, I want to learn more about, let's say, LLMs for retrieval, something like that. And this query, when you pass it to Google has to go and look in its database of all URLs, which is huge. Like I'm sure it's trillions. And I'll return to you only like a handful of useful ones, like usually like a couple of pages of like Google results, but there will be like a couple of hundred links, like hundreds. But in reality, the actual corpora is trillions, as we talk about. And this is whether Google search or YouTube videos, you go and search on the YouTube query bar, like, hey, I want videos related to LLMs and recommendation agents or something like that. This is Spotify, Amazon, Instacart, anywhere you go, basically you want to search and there's a large possible set of items. You want to only get the most related ones. That's where retrieval comes into play. And retrieval is basically the first stage in both search and recommendation engines. So whenever I maybe mentioned about the search, but whenever in recommendations as well, you want to like recommend something to the user, there will be like several steps in doing so. First, you have to like retrieve related items, possible related items, and then you will rank these items. And search and recommendations are pretty close in the way that in search, you have a query, as we talked about, and you go and find the related items to that query. But in recommendation, instead of like a query, you have a user profile. and their purchases or their likes or dislikes and whatnot. And you use that in a way, not exactly, but in a way you use user profile as a query against your whole database to bring related items for that user. So the tasks, I always think search and recommendation is kind of the same tasks. It's just that the way we are looking at the query for search and recommendation is different. But their essence is the same steps. Hey, you have a retrieval, then you have ranking. So basically then, first for recommending items to the user, you have the user profile and you encode it somehow with different methods into like an encoded version, and you run this encoded version against your database, and from there you get a handful of like items that might be related to this user. So again, this database can be billions or trillions, and what you return is in the order of hundreds for the user. Okay, so now that we know retrieval is essential and for search and recommendation, we can look at a history of like retrieval. We have like older methods like BM25 and TF-IDF, and the idea of these methods was, hey, using like counting a certain important keywords that happen between the query and the documents, we will find the most relevant documents. Like if your query, this user query, includes certain words, we will look for the document that has those words, and we will find the document that has that word the most or has the words proportionately more than other documents. Like if a document of like a one page has that word 10 times, it will be like idea of TF-IDF and BM25 is like, yeah, basically if a one page document talks about a word 10 times, it can be even more important than a document of 100 page that talks about the word 10 times. Won't go into these details here too much. There is a lot of like resources about how TF-IDF and BM25 and algorithms like that work, but I'll just quickly mention their pro and cons. Like pro is very fast. Like as I mentioned, it just looks for, hey, how many times this like word happened in this document, and then it's simple calculations. But the problem with the disadvantage cons of using this method is it lacks semantic understanding. And what I mean by that is like you have a query like this, how to bake croissants, and you may miss, if you're using like TF-IDF and BM25, what will happen is you may miss a document that says making pastries at home. And we understand as humans that croissants are a type of, say, pastries. However, this TF-IDF, and BM25 may not understand this because the words between the query and the words in the title of that document, making pastries at home, do not, basically are not shared. They're not common words between these two. So it will be missed. That's one big problem with these type of algorithms. Okay. So then, because of these problems, and as deep learning and machine learning advanced, more modern methods were introduced. Like examples of it are here, DPR, ANC, Colbert. And the idea is we will use neural networks to encode documents and queries or user profiles. Again, I'm trying to keep you thinking about search and recommendation. And practically, usually there's like a two-tower architecture. We have like a photo of it here. And this two-tower architecture, one tower is input from user, the other is all set of possible documents. And let's say your question here is the query that you search into Google. Hey, like I want to make croissants, something like that. Hey, croissants. And then here, document can be like every document in your library. Basically, there is like how to make pastries at home. Pastries. Anyways. And the idea is if this two-tower architecture is trained well, the similarity score between related documents and a query should be high. So one tower here, as we see it on the left, green tower, let's just call it green tower, will do the encoding for your query, and the blue tower will do the encoding for the document title or the whole document. And the score will be something between 0 to 1, usually. And the closer to 1, it means those two are more related to each other. The further means they are like unrelated. So the pros of this method is that there is semantic understanding because it's a neural network, a language model even. It has understanding the embedding that it creates, has like embedding for pastry and embedding for croissants are close to each other. It has semantic understanding, so problems with like not sharing the same words will not happen. However, the problem is there's a few problems with that. One of them is like you have to have a storage that keeps all these embeddings. Like imagine you have like billions of documents in your library. You have to have a storage and like save their embeddings in a storage for quick lookup. So it's costly. It's not cheap to do this. And if you decide to improve your encoder, like this two-tower architecture, if you decide to like, hey, there's a new model. Like I was using BERT, now I want to use Transformer T5. You have to basically rebuild the whole database. So again, it's not easy and it's costly. You have to update everything. And as the document length increases, your performance decreases. Like there is so much that there's a lot of research papers these days showing that embeddings of certain size can only help you with retrieval of certain number of documents, not infinite number of documents. So there are two problems, but you're definitely prefer to all their sparse methods that we talked about. Okay, so now we get to generative information retrieval, would be our main topic. And the idea is simple. The idea is instead of, hey, calculating embeddings, looking for like word count, whatnot, we just directly ask an LLM to return to us all the potentially useful documents. So LLM will directly output document names or document IDs, and call them doc IDs here. And LLM will receive as input whether your search query or in terms of like recommendation system, it will receive the user profile. And user profile would be their persona. Maybe, hey, this user likes to buy fantasy books, or hey, this user has purchased all these items before. So user history, basically. And from here on, I'll focus more on LLMs for like recommendation rather than search. But as we talked previously in the video, the idea is quite similar. Here you can see an example. This is from a interesting paper. I would suggest reading it. It's a good survey of like using LLM as a recommendation. And you can see like all these different methods of using LLMs for this task of recommendation. And by recommendation, here we are kind of retrieval and recommendation. I'm kind of using them in the same context that, hey, if we can retrieve related items for a user, we're kind of succeeding as a recommendation as well. I'm not considering a ranking for the time being. I'm just considering, hey, if we can retrieve the most related items for a user, let's say we have succeeded at recommendation. But in reality, there will be different steps of ranking as well. So here we have like, for example, blue box. There is like 5. There's watch history given here. Then like ask the LLM what field user be most interested, or there's rankings given to the LLM. Hey, like user has ranked these movies like this. Based on this, tell us like what will user would think about John Wick Chapter 4. Or it can be conversational, like you can target, hey user, I just watched this, I Interstellar, I liked it, what will I like next, something like that. And then explanation generation is like, hey, user like this, tell us why. This is useful, like the last case. Usually when your users will ask, hey, your model is showing me this item. Why is that? And then you can generate explanation. This is because you like this and that. Like Instagram, I think, used to have it. Maybe they still do, but yeah. Okay. So yeah, as we talked about above, there is like usually ranking steps in recommendation. And this ranking step, so let's just imagine like you have retrieved, you have your, let's say, user profile. You pass it to the LLM and you ask for certain items. And from all the items in your in your database, it will return like, let's say, 100 items. We'll talk about how it can do that, how it will have access to all the items in your library. But then these 100 items needs ranking. So you have to like make sure you show them more related items at the top. So like maybe like at the ranking, you need to like bring the fourth item to the top, bring the second one like to the bottom, something like that. This ranking can be another model. Like you can use LLMs as retrieval engines and excuse me, you can use LLMs as retrieval engines and bring a lot of items for the user, but use a simpler, faster ranking algorithm, like something like a tree-based model or simpler models basically for ranking. Or you can use LLM, another LLM as ranking. So you'll have like a huge model who can do like retrieval, and then maybe a fine-tuned smaller model for ranking. Or you can have one model that will do ranking and retrieval, which is the idea here, both ranking and retrieval done by the LLM, which is an emerging area of research, pretty interesting topic. But yeah, that's how you can use basically LLMs in combination with whether an older model or with another LLM or one model to do both. And one example of how we can basically suggest items to user as both ranking and retrieval is sequential recommendations. So in this area of research, what happens is usually you would give user first purchase this item, then they purchase this item, then they purchase this item. And then you ask the LLM to predict the nth item. So you would give one from 1 to n minus 1, and then you ask for the nth item. And one example we can see here, like this is from an interesting paper, CalRec. I suggest reading it. But if you look at it, there is like user purchase history, and each one of these is an item user has, like whether interacted with. I don't remember exactly what the paper was saying, but it was whether the user purchased it. Oh yeah, sorry, it says purchase history. So yes, the user has purchased these items, and there's like title, there's category, all this information we pass to the LLM. And basically we ask for the LLM to tell us what would be the most likely next item. And then we can get that, pass it back to the LLM, ask for the next one, or instead of asking only for one item, we ask for what's the next, for example, 10 items user will purchase. And then because it's an LLM, by changing the prompt, you can do a lot, right? You can tell the LLM, hey, return the next 10 items to me, but also rank them. So ranked next 10 items that user will purchase. So in a way, it will go look at all your like database, all the items that are possible, and returns their next 10 ranked items. Okay, so we'll talk about document IDs, but semantic IDs now. We'll talk about how LLM can basically have access to all the items in your database a little bit like further down. But before we do that, I just wanted to quickly talk about semantic IDs as well. And semantic IDs are another way of representing documents by the LLM and to the LLM. So far we talked about, hey, like items having like title, and then like title is something, there is category is something like in the previous prompt we saw, and then there is like date, things like that. That can be like something that we pass the LLM. But there's a large area of research that says, hey, let's encode this information instead of just passing the LLM all this text. Let's just encode it into like simpler and more useful information for the LLM. And that's where the semantic IDs come in. And what happens is, let's think about like an example of a shoe shop. Let's remove this. And this shoe shop, let's just for the sake of simplicity say each item in this shoe shop is shown by like three things. Whether each item basically would be like, hey, red Nike shoe, or like orange Nike shoe, or something like that. Let's say orange Nike shoe. This is the title that would have previously we would have given to the LLM. But when we use semantic IDs, this orange Nike shoe can be encoded to something like let's see, semantic ID would be encoded to something like, hey, 5323, for example, something like this. And the first number might just say, hey, this is a category of items, this is shoe. Let's say you are at like a clothing store. So you may have shoes, you may have bags, you may have different things. The second number might talk about the brand, would be like Nike. That was like, this is a shoe. It says this is Nike. And this may talk about the color, for instance. And basically, we will encode it like a hierarchical encoding. So if like this was, instead of being, let's say, orange Nike shoe, it was like a red Nike shoe, the first two parts will remain the same, right? You will still know it's a shoe, you will still know it's Nike, but the third part, instead of 23, let's say, it would have been 14 or something like that. So in this way, the model also starts understanding that there is a hierarchy to these items. And one very famous method of doing so is residual quantization variational autoencoders, or for short RQVAE. And the way this RQVAE works is basically, let's say, we have an embedding model. So when you pass the orange Nike shoe to your embedding model, let's say you have like transformer T5 or something, but you have like an embedding model, you'll get an embedding vector, right? This is your embedding vector, like orange Nike shoe becomes the embedding vector, and this vector is passed to DNN. This is your embedding, and this DNN will create a smaller latent vector, right? And this RQVAE has like different code books, and by comparing like this latent vector to different vectors inside of this code book, you will find the closest vector to your vector. Let's say it's the first vector, and then you calculate the residual between your vector and the closest vector, and then you pass the residual to the second code book, and then you find the closest to the your residual, then again the residual from that third notebook, and you start building, like you start selecting indices of the closest vectors to your vector. So here, like example above, we had like 5 to 23 or something. So it means in the first code book, the closest vector to yours was the fifth one. In the second one, the closest vector to residual was the second one. The third one was the 23rd. So you start building this encoding. And I know it was like very quick, so I just wanted to like give an overall idea and didn't want to like enter it in more details. But let me know if you're interested in learning more about RQVAE. I can do a video, like a whole dedicated video on that topic. But the idea is this basically. And when you build such, when you build such index, you're still a variational autoencoder, right? So you still have like a decoding part that will try to rebuild the embedding based on your latent vector that you had. But then during inference time or during when we want to use the RKVE to do the semantic IDs, you don't need the decoder part. Anyways, back to here, just wanted to like give you like a quick overview of how that works. There's a lot of research on this. Unfortunately, not many actually videos on this, so I may just do a video about RKVAE. But here, this is from a paper from Google. It's also called Tiger method. And Tiger idea is, yes, you will have sequential user history, and you will basically do semantic IDs. Actually, it's already shown down there. So you will do sequential purchase history. And it says 523.55, this is saying, hey, orange shoes brand X, or 525.78, red shoes. And then generative retrieval will get you the next item. And this can be whether be passed to an LLM or just a very large transformer. So sometimes in this field, when you're talking about generative retrieval, it doesn't necessarily mean we're using an LLM. Sometimes it's just a very large transformer model that's learning to predict items sequentially. Okay. There is one caveat, I would say, to using semantic IDs, and that's the fact that, hey, you need to do a fine-tuning on your LLM. You can't just use the LLM out of the box. You can't just give these numbers to LLM and expect it to magically know like 523.55 what it means. So you have to do fine-tuning. And you have to also have like, of course, an encoder that basically does semantic ID for you. But yeah, I think the biggest problem is you have to do fine-tuning, and as newer like items are added, if the LLM or the transformer hasn't interacted with those, you need to do like a whole, again, another round of training. So it may not do great on cold start problems, and also it definitely needs like extra training for the neural network or the transformer or the LLM to do well with this. But the advantages is that, hey, you save on tokens, you don't have to give long like descriptions to the LLM, and when you learn the semantic IDs, the model is learning it like learning a hierarchical structure, which is more meaningful than just titles. Like understanding 525 always means like shoe of certain brand. It can be super helpful to the model to learn that in a hierarchy rather than just learning the titles. Okay, so far we talked about how we can use LLMs to like predict the next item from predict or retrieve. Let's say retrieve the next, retrieve the items, the related items to what you want. Or you can use semantic IDs to do this. However, there is a problem that you may ask, hey, how can LLM have access to all that there is in my database, right? You may have, as we discussed, a database of like billions of products or trillions of URLs. You can't just pass all of this to the LLM and expect it to select from there, right? Because one method you can do is, basically what you can do is say, okay. One thing you can do is like basically have your prompt and and in this prompt that you have, you will start giving all the possible items to LLM to select from, right? You will have item 1, item 2, item 3, and you tell the LLM, these are all the items in my database. And this is user profile, and this is all the items in my database. Now, based on user profile and based on the items, like output what items this user might be most interested. Like it may say item 1, item like 10, something like that. Or instead of profile, you may say, hey, this is a query. So based on this query, what items should be retrieved? And again, LLM would say something like this. But as we all know, it's impractical. You cannot expect to pass 1 trillion URLs to the LLM and expect it to like basically select from them, or 1 trillion like book titles and expect the LLM to be able to keep it in its prompt. So that's basically not possible. The second problem is when you're asking the LLM to like output items, you're asking for LLM to select from the shoes, right? You have all the shoes, and let's say this is the LLM and has all the shoes and has user profile, all that stuff that's necessary, and let's say they all fit. There is enough context window to keep everything that you have in the LLM. Let's say your application is simple. You have only 1,000 category or something that you need to fit in the LLM. But still there's a problem. And the problem is we have a red Nike running shoe, which is an actual item in our database. We have it. If you go and look for this item, you'll find it. But what if the LLM starts saying something like red Puma or even red Nike, but instead of running it says exercise, right? And what is the problem here? The problem is the red Puma shoe or red Nike exercise shoe may not exist in your database, right? What do we call this problem? Like, well, what we call this problem is, as you all probably know, hallucination. So LLM made it up, hallucinated these items when they did not even exist. So we have two problems then. One is we have limitation on basically the prompt lengths. We cannot pass everything to the LLM. And second, we have problem of hallucination. What can we do? What we can do here is use a method called constraint decoding, or it has different names: constraint decoding, constraint generation, guided generation, guided decoding. There's all these names for it. But the idea is simple. The idea is you limit the LLM only to certain possible tokens. And we define a prefix tree, or also called try tree. And there's a picture of it here. This is your root node. This is the root. This is where LLM wants to first start generating something. So given user profile, the LLM decides that the next item I should show this user should be red Nike running shoes, right? So LLM starts by the first word. Here, for the sake of simplicity, we say each word is a token, which is not exactly true. But let's say here, LLM first token comes out red. Okay, so LLM now looked at all the possible places it could have gone, and it wanted to start with red Nike shoe. So it managed to select red. Then here you look, here it looks at all the other possible ways it can go. And there is Nike, there is Puma. So if it wanted to suggest Nike or Puma, it would have been fine either ways. It was allowed because it is in your DB. So, but let's say the model wanted to, instead of Puma, say like some other brand, for instance, let's say brand X, right? And brand X doesn't exist in your database. So what happens? So LLM wants to say a red X running shoe, but X is not possible for the LLM to select from, right? Because only possible tokens, or like here for the simplicity, only possible words that can come after the red is Nike, Puma, or like other words that we have allowed the LLM to select from. But when I want to say red X, the X is not even possible to select from. So the LLM doesn't even consider it. So no longer you will get like a random, let's say random brand that doesn't even exist in your database. So you go to red Nike and then says, okay, I said red Nike, and then instead of like running, we talked about, hey, it may say exercise, right? But when it wants to go to exercise, there is no exercise, right? So the only thing to select from is whether running or let's say something else like workout or something. So basically the LLM cannot output something that's not in your database. So it's like putting the model on train tracks. It means it can move, but only in certain directions that we allow it. So by building this tree on our own database, on our catalog of like items or possible things that LLM can select from, we restrict the LLM's generation to only things we allow it to. So hallucination basically goes to zero. That's one good thing about constraint generation. The second thing is like we could not pass like everything item to the LLM context, right? But now LLM can basically output anything on our database without even having to pass all of it to tell the LLM, hey, select from. Why? Because we tell the LLM, hey, let's generate the next possible item. And if previously we had to pass all the possible items so LLM can select from, but let's say as LLM starts generating an item, but using the constraint generation, it can only generate a valid item, right? So in a way, now it has access to output anything that it thinks is potentially the next item the user wants or the item is looking for. But at the same time, what happens is the item that comes out is only a valid item, right? So in a way, without having to pass all the items to the prompt, you allow the LLM to select any item from your catalog, and it's always a valid item. This is also extremely useful when you have already fine-tuned your LLM and it has kind of seen what is possible, what is on your catalog, and now it can start selecting from it. The idea of basically semantic IDs with constraint generation is the same, but instead of, let's say, red Nike shoe there's root, wants to says in red Nike shoe, it can only say 5, then after 5 it can only says 23, then it can says, right, something else, right? Excuse me. So the same idea applies, but only instead of words or tokens here, you have numbers. Like instead of like red Nike shoe, it could have gone for Puma or something like that. It could have gone to 25, but it basically, LLMs will only output numbers rather than anything else. So you make sure LLM doesn't output anything random, and the numbers, the ordering of numbers is something that's valid. It cannot output, hey, 2,100, then 30,000, right? It never happens, because it can only, when it's starting from root, it can go to 5 or like 1 or something like that. Okay, so putting it all together, We saw how we can use LLMs for retrieval and recommendation. We can basically ask the LLM to generate items for us directly. Hey, what would the user would be interested? Give me 10 items or give me 1 item. We saw how we can use basically semantic IDs, but the idea was the same thing. Whether search or recommendation, you give the LLM what you're looking for, the user profile or user query, and you ask the LLM to basically give you items. And using constraint generation, you make sure the items are always valid. LLM doesn't hallucinate anything. And fine-tuning LLM can definitely improve this process, especially if you're using semantic IDs. But if you fine-tune the LLM, it will slowly see all the items in your, or at least a good portion of items in your database. And then when it starts doing like generations, it has a better idea of what actually exists. And the token probabilities for existing items also increases. Okay, and yes, but this is not, I'm not advocating here to deprecate all the older like embedding based systems and then use an LLM. This is not a replacement for like older retrieval systems that work very fast, because well, we know LLMs are slow, they're costly, but where it feels really shiny is an example like, hey, if you search for Toronto weather today, it's very easy for Google to just find the most related like URLs, because there is like Toronto in there and there is weather. It's very simple search. But if you search, show me some places for a 2-day trip in Toronto with family-friendly activities near a lake. Now, this is not something that a simpler retrieval engine can handle easily. You have to understand different things. You have to understand, hey, this is a 2-day thing. You have to understand it's you have to go to Toronto, it has to be family friendly, and then the LLM can understand what is family friendly, what like a simpler model doesn't. And then there is near a lake, and on top of that, you may also pass the user profile with this search query. Hey, this is our user, this is what places has been gone. Let's imagine it's like Airbnb or something. These are all the previous places they have gone. This is what they like, this is what they dislike. And the bigger models always do better. Like it's something like a GPT-5 model might like actually outperform all the traditional recommendation and retrieval engines. Like I've done some experiments on like a few like different use cases, and I have seen that even like a GPT-5 model with no fine-tuning whatnot is able to like outperform tree-based models that are exactly trained on that task. But maybe a small like 1 billion llama model may not be able to do that without fine-tuning. So fine-tuning definitely helps in this scenario, but if you don't do it, you can still use this generative retrieval method with like a large LLM, and using constraint generation, you make sure the items are valid. So parting thoughts. I've been to a few conferences past year and like been to a few different events. This is definitely an area that's getting more and more attention. And a lot of companies like Netflix, Google, Meta are like already investing into this. Like this year I went to KDD 25 conference, and there was a lot of presentations already talking about this generative retrieval topic from these companies. And there is a lot of like research as well showing these methods like this LLM as a recommendation and retrieval can actually outperform older methods. Like I mentioned a few of them here. Feel free to like read these papers. Like they're very helpful. Like the Tiger method we talked about, like 29% improvement in this CG5 Amazon Beauty dataset. So there is definitely evidence now that these methods can work even better than traditional ones, but this is still a new area, and we are early in this shift. And still, for maybe a smaller startups or maybe a smaller places that can't afford to run LLMs, this still is probably not a practical thing to use, but definitely something that the larger players are using and investing and researching on. I left some essential reads here. I suggest definitely going through them if you want to learn more. Okay, that's it for today. If you enjoyed this video, please consider subscribing so you don't miss the next videos I upload. And if you think somebody else will benefit from this video, please share it with them. And in the next video, I'll go through how to use LLM to build a simple recommendation model using a open weight large language model. And please feel free to drop any comments or questions in the comment section. I'll try to go through all of them and answer any questions. With that being said, thanks for watching, and I'll see you in the next video.